Hello everyone, welcome back. It's my pleasure to introduce our next speaker. Catherine Turner is an associate professor in the Mathematical Sciences Institute at the Australian National University and a member of the Mathematical Foundations of Data Science Center within MSI. She received her PhD from the University of Chicago in 2015. She had a postdoctoral position at EPFL in a joint position between mathematical statistics and the Laboratory for Topology and Neuroscience. She moved to ANU in 2017, and Kate uses topological tools to analyze data, and she proves mathematical foundations needed for statistically rigorous analysis of topological features. So welcome, Kate. Thank you.
All the organizers for having me here and giving me this opportunity to try and convert you all to the world of theoretical applied topology. Okay, so before I start, I apologize for the very long title. It's excessively long. I just want to make a few comments about how this relates to the previous plenary talk by Priya. So at the very end, there was a glimpse of persistent homology there. And she was talking about sort of sub-level set filtrations, as if you had a mountain range and you were filling it up with water and you looked at how the topology of the sort of surface of the water kind of changes as you raised that level. Okay, and this is a great way to use persistent homology, but it is not the way we're using it in this talk. Okay, so I'm just going to make that clarification before I start to sort of preempt any confusion. Okay, so I will be talking about Rips filtrations. So here I've written what Rips and check filtrations are. So the kind of data that you're using for this is when you're given, say, a point cloud in some Euclidean space, or you're given a finite metric space, okay? And you have a set of points, and you want to build an increasing family of simplicial complexes. And each of these simplicial complexes will correspond to some sort of length scale R. And the idea is that for Rips, you include a simplex, okay? So if you're not familiar with topology, think edges, think triangles. Whenever pairwise, all the distances are less than 2R or R, depending upon how you want to do your scaling. And then on this side here with the check, you have a slightly different rule. Okay, you include a simplex when the balls have a non-empty intersection. So not just pairwise non-empty, but overall non-empty. Okay, so these are the kinds of constructions we're going to be making. But Rips point clouds, the kind of data, the data structure we're going to be building, can be done in a more general setting. And this is sort of the most general setting that you can do it in, unless you go to something crazy and directed. You have some finite set, and then you have some sort of symmetric function over your set, such that you never get the pair before you get the endpoints. Okay, and this rule is required so that you get points before you get edges between those points. Okay, and the rule becomes the same. It's just instead of doing distance, I go the function value for the pair. Okay? Now, if you don't want to think this way, ignore this for the rest of the talk. Point clouds in R2 and R3 are totally fine. Okay? So I will have to give you a crash course in algebraic topology, but it's going to be, you know, the nice, happy version where everything is over Z2. This is partially because it makes things easier to describe, but also because we will later be using computers, and computers like Z2. Okay? So we have things called cycles, and I'm only looking at degree 1 homology, so I'm only going to care about 1 cycles. And this is related to when you think about the cycle of a graph. Okay? And so the way we define it is it's going to be some Z2 formal linear combinations. Everything's in it or it's not. Okay, of the edges within your simplicial complex, okay? So such that each vertex appears an even number of times. Okay, so this side here is a cycle. Here, x2, 2 edges. x4, 4 edges. x5, no edges. That's a cycle. This, not a cycle. x1, 1 edge, okay? So they can be disconnected, that's not the issue. It's just a matter of whether or not you have an odd or even number of edges out of each vertex, okay? The other ingredient we need to know is boundaries, okay? So boundaries are boundaries, okay? It's a good name. You take triangles, and then you look at what's in the boundary of that set of triangles. Okay, so here I've taken one triangle and its boundary are the 3 edges. Okay, I come here, I take 2 triangles, I take its boundary, I get these 4 edges. Okay, now this one in the middle, it's the boundary of both triangles, so they kind of cancel out. All right, but if I was to do 3 triangles here, I do put that one in the middle back in because 3 is odd. Yeah? Okay, so boundaries are things that are in the image of this map that goes from sets of triangles to sets of edges. Okay? So those are the 2 ingredients we need to be able to define the degree 1 homology. So the degree 1 homology of some simplicial complex, which for us is just vertices, edges, and triangles, okay, is going to be the boundaries mod the cycles. Okay, so we can take this quotient because the boundaries are contained in the cycles. So we just take this quotient, and we can think of these as Z2 vector spaces and the Z2 vector space that is their quotient, or you can write it with sort of coset sort of notation, which can be helpful. Okay, so hopefully this is kind of okay, but pictures say 1,000 words. So what I've got here is I've got an example of cycle here, which are in the same equivalence class. Okay, we could say they're homologous. Okay, so they're in the same homology class because they differ by boundaries. Okay, so hopefully, I really apologize to anyone who's colorblind if this is hard to see. Now I did say this is also a vector space, so we can do addition. Okay, so I can add 2 homology classes together. And I think this may be the only equation in all my slides. So I have this homology cycle plus this homology cycle. And then when I add them together, these ones on the edge, they cancel out. Okay? And I could write this in many ways, but this is one representative, and that's all we need. Okay? Whenever I have one simplicial complex inside another simplicial complex, we can think of that as being like an inclusion map. Okay, I've got one included into the other. Okay, and whenever I have this kind of map, I automatically have that the cycles in the smaller one are still cycles, and the boundaries are still boundaries. Okay, and this means that I can have this well-defined map that takes some homology class in K and sends it to a homology class in L. Okay? So here is an example. I have this red homology class. I send it into this. So this is K, this is L. And this one here is actually equivalent to sort of the empty, the 0 homology cycle, okay? So we could say that this is in the kernel, or equivalently just this bit here. That's in the kernel, okay? And I can also look at the co-kernel of this map, and these are cycles that appear in L that aren't in the image from K, okay? And so you can see that there's this cycle here, okay, this cycle here, that just isn't in K, okay? So what we care about in applied topology are these, the homology classes that persist through different inclusions, okay? So this leads to the definition of persistent homology. So in a way, it would have made a lot more sense if the orders of the talk this morning were switched. So we have an increasing sequence of simplicial complexes, okay? And here I've got them indexed by numbers, but they can really, they're going to correspond to real length spaces. That should be an Rn. And then the output is going to be a sequence of homology classes plus all these induced maps by inclusion. And this, as an algebraic object, is sort of our persistent homology, okay? But if I'm wanting to apply this to data science, I don't want to give my domain expert, my biologist, this algebraic object. This is not going to be helpful for them. So instead, what we do is we use representation theory to say, all right, there is a nice representation of the algebra here, which is unique, up to reordering of the indices of these little bars. So each of these bars here corresponds to some sort of persistent homology class, okay? Some sort of cycle in my space, okay, that lives over a range of length scales, okay? So these here correspond to these different circles here. So there's 12 little circles here, and each of them gets its own little line. And the birth, okay, is the radius at which these line up to make a little circle, and the death is where they collapse to just be a blob. Okay, once things become a blob, they die, nothing interesting happens. And then this long cycle here corresponds to that big circle, okay? And it's born when these bits link up, and it dies when it's all a big blob, okay? So this means that this description here can tell us how the homology persists through different length scales and is sort of a multi-scale approach. Now, there was a bit of a divide, maybe in the 2000s-ish, between East and West Coast of America. East Coast, led by the Duke crowd, drew things with persistence diagrams, which are the things that Priya showed in her talk. Stanford was a fan of the barcode, which is this. Both are equivalent pieces of information. You just use whatever suits your particular needs, but they're the same. So those things with the long triangle and points, each point corresponded to one of those. Just to link back to the previous talk. Okay, so this is persistent homology. I've defined it to you. You're all experts now, okay? So this is my Bluey reference. So I have this definition of persistent homology, and I can define for a point cloud or an arbitrary symmetric matrix this filtration of spaces that I can calculate as persistent homology. Now, I, as a mathematician, find it interesting in of its own right, but some people prefer to have extra external motivation, and that's totally fine. So Rips filtrations are used they're almost ubiquitous in the topological data analysis world. So I've just picked some random ones mainly because they had pictures. So one example here is a cosmology paper I picked up, and this is to do with dark matter halos, and I quickly got lost in the astrophysics, but it's a very beautiful picture. This one over here is about looking at the shapes of proteins and how they knot. And so knots relate to cycles when you take, say, a point. You sort of take your protein and then you dot lots of points on it, I guess to do with where the atoms are, and then you grow the balls around them, do your Rips filtration, and then you can look at loops over that point cloud. And then that tells you something about the configuration of the protein, okay? And I put this one in here, even though it doesn't have as good a picture, just to illustrate that beyond point cloud situation. So here is something to do with inhaled substance abuse. We're lovely here. So one of them is control and one of them are patients. And they had fMRI data, and then they were looking at co-activation of different parts of the brain and looking at the correlation. So from correlation, you can make a dissimilarity function. It's not going to satisfy the triangle inequality, but you can still do Rips filtrations for it, and that's fine. And this is sort of showing how the barcodes look different, somehow representing how the structure of the brain is happening in a different way, okay? So these are some examples. So the Rips filtration and its persistent homology are kind of very easy to state as mathematical objects, okay? You can explain it to someone very quickly. It's beautiful, it's lovely, it's nice. Computing it, on the other hand, for when you have something which is non-trivial in size, becomes much more difficult, okay? So it's one thing to say it, it's quite another to run it, okay? So I wanted to have a few comments about sort of the inherent computational complexity of the problem. So if I'm doing degree 1, persistent homology, okay, higher order degrees, it's even worse. If I'm doing degree 1 persistent homology, then I only need to know the vertices, the edges, and the triangles. And if I have n points, then I'm going to have n vertices, I'll have n choose 2 edges, and I'll have n choose 3 triangles. Okay, because I'm going to put everything in at some point, I'm going to have all of those. So I'm getting n cubed. Okay, order n cubed is the size of my complex. Okay? And then the persistent homology algorithm is you take capital N simplices, and it's sort of, if you just take the standard algorithm, okay, you're going to get capital N cubed as your worst case running time. It's sort of the inherent cost of doing business in persistent homology, okay? And so overall, we're getting little n to the 9. This is not a happy space, okay? Now, I'm not going to go through the persistent homology algorithm. Now, yes, there are probably, there are things tweaks you can do to make it slightly faster. You can stick in some heuristics, et cetera, but this is not the topic of today's talk, okay? Because I'm not worrying about a paradigm where I make this better, okay? I'm going to care about this, all right? So before we start, we want to set the benchmarks, all right? We want to understand how bad is it, okay? And I'm not expecting you to read all this table, okay? The thing that matters is the fact that the complexes this is going, so this is a benchmarking paper that Nina Otter wrote with others. I guess they wrote it in 2015 and then it got published in 2017. And it compared all the available software at the time, okay? So there's a few more since then, but this was what was available at the time. And they ran it on a cluster. So this is my observation too. Like, this is not just any old desktop computer. They're running on big things, okay? And they ran it on a bunch, and all those little lines here, they correspond to when it just ran out of time or ran out of memory. It just couldn't cope. It was too big, okay? And these aren't big things, okay? This is the size of the complex. The number of vertices is much smaller. That's the largest data set. That's the Dragon 2. Most of them are more like 1,000 or a few hundred. We're not looking at really large data sets that you're sticking in. Okay? And the other comment I wanted to make is that RIPSA is clearly the winner. It's become almost synonymous in the community with Rips Filtrations. It's just the fast one. It's the memory efficient one. That's the one everyone uses. So when we do any comparison, we're going to compare to RIPSA. So you might say, oh, well, that was 2017. That was a long time ago. It's the dark ages. It must be better now. This is still not now, but this is a little bit later. This was another benchmarking paper that happened in 2021. And this was comparing things in R, okay? Because statisticians like R, so they were talking about different things available in R. And so these were the 3 available at the time on R. RIPSA, implemented for R, or I guess it's got bindings for R. Dionysus, and there was a Goody one. And, again, RIPSA is clearly winning. But the thing I really want to care about is this number, okay? This is the problem. I mean, we're espousing that we're going to be the solution for big data. And 500 just ain't big data. And then these ones aren't even making it past 300. So we need to do better, okay? So we want to take lessons from other things. We want to leave the land of Rips and see what other complexes do. How do they work better? And this is why I defined the check earlier. It wasn't completely random. It's because we're going to learn a lesson from check, okay? So the alpha complex and the check complex have been long studied by people in computational geometry, okay? So people may have seen a Voronoi diagram before. The idea is that for every point, you draw the region in space for which it is the closest point, okay? And then you can do a triangulation of space by taking the dual of this, okay? And so this is the Voronoi diagram, and this is the Delaunay triangulation. Now, if you want to do the alpha complex, you just take the check complex, but you intersect it with this triangulation. So you don't include everything, you just include those triangles in this triangulation of the plane, okay? And the advantage of this is it has far smaller, fewer simplices. You know when I said it had n squared, n choose 2, n choose 3 for the Rips? Not the case for the Delaunay triangulation. You're good, much smaller, okay? And basically the nerve lemma, okay, tells you that you're going to get the same persistent homology. Okay, so you get a win. You say, well, instead of doing check, I'm going to do alpha. All right? Now, the only caveat here is the Delaunay triangulation is hard to compute for high dimensions. It's great in 2, great in 3, it's okay in 4, and then after that, but we can still learn from this lesson. Okay, so that's the plan. We're going to learn from this lesson. So just to show you, this is back in that benchmarking paper, and I talked about, so this was Goody Rips. Goody also has an alpha filtration, so it's the same software package. Here they're looking, this is just the object size, it's not the running time. It's just saying, well, if I have this many points, how many simplices are there that I need to use to compute the persistent homology? And you can just see that the savings you get from using the alpha complexes are dramatic. Okay, this is a win we want to have. Okay? So this is going to set us up for our new computational paradigm. Okay? So what are we going to do? We're going to recognize, first step is, acknowledge the problem. So we're going to acknowledge the problem that we don't want to compute the persistent homology of the actual complex. We don't want that. We only want to know it up to isomorphism. Okay, so that is okay. We just need to do the isomorphism type. Okay, and the next thing we want to do is we want to do that Delaunay triangulation. We want to find some complex that plays that role and intersect our normal Vietoris Rips filtration with that so that we get the same homology. Okay, the same persistent homology, all right? So this is like the check trip. This is the check trip. And then the third thing we want to do is know when to stop. So at some point, at some threshold, certainly be long before, the diameter of the set of points is definitely it's going to happen, but probably a lot before that, you're going to get a blob. Okay, your points are just going to be a boring blob, no homology, nothing interesting happening. And you want to know when that happens, because once that happens, you can say everything is 0. They're all dead, Dave. They're all dead. Okay? So these are the two sort of tricks we want to have in order to sort of have a new way of approaching this computation. So the ingredient we need is the loon of an edge. So I'll put a little asterisk here. This is the definition for when we have unique pairwise distances. If you don't have unique pairwise distances, you have to do a little, tie-breaking trick in there. It's not actually that different. For the purposes of this talk, everything is unique pairwise. That is generically true. So the loon of an edge is a classic thing in computational geometry. We are not claiming anything new. But the idea is that you take an edge, okay, you take these 2 points, and we look at the balls around each of them, of that radius, and you say, when am I in both of them? So here Z is the loon, W is not. Yeah? Good. That's the definition of the loon. The next thing we're going to do is we're going to look at the connected components in the loon. Okay, so here I have points not in the loon, and in the loon. Okay? And then what I want to do is I take any 2 points of the loon, I compare the distance between them to that distance between Y and Z. Okay? And so whenever that distance is less than that distance, I connect them together. And so here I have 2 connected components, one down here and one up there. Okay? The vast majority of the time you'll have a single connected component. I had to, massage this to get 2. All right? And the next thing I'm going to do is I'm going to pick a representative from each. Okay? Because I don't really care which one. It doesn't matter. I just want to be consistent. Okay? So I'm just going to denote by capital L my set of representatives. Okay? So it's either empty, it's got 1, it's got 2, whatever. Okay? And I guess I should mention here that if I'm in R2, the max I can have is 2. If I'm in R3, the max I can have is 5. and so on and so forth. So in all Euclidean spaces, there's some finite bound on how many you can have. And this is also true for these doubling dimension spaces. So it's a reasonably standard condition that you have for metric spaces that there's only going to be finitely many, like a finite bound on what this can be. All right. So now I can introduce our reduced Rips, okay? We've reduced it, it's gone on a diet. We acknowledge that there are n vertices, n choose 2 edges, n choose 3 triangles. So the triangles are the problem. Okay, they're the ones we think are the real problem. So we're going to say, all right, we'll cop the n choose 2. We'll include both the vertices and all the edges. But then we won't include all the triangles, okay? All we're going to do is have one triangle for each of those connected components in the loon, okay? And then we define our reduced Rips in that intersection way, using the check trick, okay? So here is an example. My loon, okay, so this is the same loon. I copied and pasted. I'm that smart. So when I put in this edge, okay, I am also going to put in 2 triangles. Not 5, but 2. There's a saving, all right? So I'm not going to give proofs, but I want to make a few comments as to why the persistent homology is the same, okay? So the first I'm going to observe is that every map anywhere is induced by inclusion. So with the persistent homology, for it to be equal, I need not only the homology classes to be equal, but also that the isomorphisms on the homology commute with the induced maps by inclusion, and we get that for free. So that's good. The second thing I want to observe is by taking all the edges, we got the cycles were the same for free. Okay, so all you need to do is show that every boundary in the Viator Rips can be generated from boundaries in the reduced Rips. And this comes down to basically induction proofs. Okay? All right, knowing when to stop. All right, so this was the second trick, and this gives massive savings. So in the Rips algorithm, the leading man in the competition, it has an acknowledgement that knowing when to stop is a useful thing. But in order to do this, it doesn't calculate when to stop. It tells the user, hey, tell me the threshold at which you want me to stop as its option. And if you don't put it in, it defaults to the radius. So it's definitely worthwhile doing. Now, the advantage of what we're going to do is that we have a stopping criteria to guarantee we've got everything, as opposed to hoping some threshold will work. Okay, so our trick is to use the relative neighborhood graph. Again, a standard thing from computational geometry. All right, and I believe that when this was defined, it was described as the way that your mind would automatically create a graph. Okay, you can also think of it as the way you would draw a constellation. Okay, so you add an edge to this relative neighborhood graph exactly when the loon is empty. Okay? So if I look at any of these points, and assuming I drew this correctly, because it was by hand, if I drew the loons, they would be empty. And anytime I didn't put an edge in, say this one here, it's clearly there's a point in the loon. Okay? Now, the useful fact is that every cycle in the Viator Rips complex is going to be equivalent to some cycle in the relative neighborhood graph. So this means that when we're looking at that persistent homology with all those bars, we know exactly how many bars there's going to be, because every bar must correspond to some cycle in this. Okay? So all we need to do is compute the RNG, find its cycles, and then every time we add a triangle, we just check. Have I killed everything yet? And when I have, when everything has become a boundary, I just stop, because I know the homology is going to be 0 from then on. Okay? So this is the bit where I sort of weep at the gap between theory and implementation, okay? So in theory, This will work for any point cloud at any ambient dimension. It will work for any symmetric matrix with that condition that the diagonal is always less than the off diagonal. There are analogues to degree 1, which I haven't described here, but exist, that will mean we can do this for any homology degree. What have we actually computed? Point clouds in R2 and R3 in degree 1. But you know, step by step. The other thing I want to mention before I put in some of the graphs is, set the scene. So you know that when you have a graduate student come and start, they go to the storeroom, they get out some computer, they give it to them on their desk. That's the computer we're using. We are a bunch of mathematicians cosplaying as computer scientists. We don't know the correct data structure half the time that we really should be using. Nothing has been truly optimized. So let's just set the scene with that. Now I can put this in. So this is that Dragon data set that was in the benchmarking paper. So it actually came from a much bigger data set, I think in the Stanford repository of stuff, which you then subsample. So we can subsample with 1,000 points, we can subsample with 10,000 points, however many you choose. Okay, and the blue is RIPSA, the red is us. Okay, so I'm going to make a few comments. You don't need to look at this in great detail, but the key thing is that the blue stops. Okay, the blue stops because at some point our computer just can't cope. It runs out of memory. Okay, and that's because RIPSA needs to put the whole simplicial complex in. It's an inherent flaw. Okay, if you've got a big complex and it's bigger than the memory of your computer, you're doomed. Okay, the other thing is that RIPSA is slightly faster when they both run, but RIPSA is a decade old. It's written by computer scientists. It's an unfair playing field to start with. RIPSA is also written for much more generality than it points in R2 and R3. So I should clarify that right now. It is a more general software. Keep using it. The other example I wanted to do was random points in a cube. So I could go 1,000,000 points. So here is the million. And there are two things I wanted to mention. One is we are slightly cheating because the knowing when to stop kicks in quite early when you do random point clouds. So we are slightly cheating. I want to give that caveat. The other thing I wanted to point out is that once you have large point clouds, that is a 1.02, I think. Is that right? Yeah, good. Oh yeah, I can see it better here. We are effectively getting one triangle per edge. The vast, vast majority of the time you have a single connected component, you're just adding one triangle, okay? Now this is the talk I gave at Sydney Uni a while back, and I wasn't allowed to give any more details, but now I am allowed because this morning on archive, the paper was submitted for the next stage. Nothing like a deadline. So, we can do better. So let's stay at that because, we've got to do that. As I said, we had one triangle per edge. So clearly, if we're including every edge, we can't do better. But there was no reason why we had to do every edge. We were being lazy. We wanted the cycles to be cycles, not have to worry about it. But there's not actually a need to have all the edges. Many of these edges will be attached to triangles and sort of go to nowhere and don't really play a role in becoming boundaries, which is what they need to do. Okay? So what do we want? We want to use discrete Morse theory, discrete vector fields, to figure out which triangles are the ones we actually want. Okay? So for each edge not in the RNG, we're going to pick one connected component. Most of the time we have no choice. Occasionally we might have choice. And anything that's remaining is called a critical triangle. Okay, so the vast majority of triangles are paired up with the edge that comes in at the same time as it, and every so often we have an extra free agent triangle which we call critical. Okay, and every persistent homology class will die when the corresponding critical cell is added. So adding this critical triangle corresponds to some death. Okay, and what we're going to do is we're going to flow follow the flow on the vectors to reach the other triangles and see which ones we want to keep. So here is just a picture of choosing this vector field. So here is my edge WZ. I have a single connected component. No choice, that's the one I go. Okay, so I'm staying in reduced Rips, so I only have one triangle. I pair it with that. Over here, I have those two components, so I pair with one of them and the other is deemed critical. Okay? And so now I'm going to introduce the distilled Rips filtration. I've distilled it to its core, okay? And we look at the critical triangles and everything that I can get to by following flows, okay? So I get a subset of the triangles in the reduced Rips. Only the ones that I actually need in order to build these boundaries, okay? And then when we do the check trip again, we just do the intersection with this subcomplex instead of the full reduced Rips, okay? So why is this equivalent, okay? So I should have probably put this at the top. We're not using Morse homology, but we are exploiting Morse homology. Okay, so for those who know about Morse homology, you can have critical cells of your triangles, and you have critical edges, which for us are all the things in the R and G. And then you can look about for every critical cell for every critical triangle, you follow the flow down, and you look at how many paths can I go from the triangle down to the edge. And that's the coefficient you put in front of that edge. Okay? Now this is all well and good in the pictures I showed because there's one nice path to everything in that bounding circle. But if I'm in a more complicated space, it becomes pretty awful bookkeeping because you can have paths that diverge, you can have multiple triangles going to the same edge, and so you have to keep count of all these different paths. And that's pretty awful. Simplicial homology, which is the thing the normal persistent homology algorithm calculates, is much more straightforward. You have a boundary matrix, you do some matrix operations, and we're all happy and go home. But there is relationships between the Morse homology and the simplicial homology. And so it's those relationships that we're exploiting. Okay? So although we define this distilled Rips complex via the persistent via the Morse theory, we actually just define a simplicial complex and do normal simplicial homology. But it turns out that the Morse homology of this and the Morse homology of that are the same. And thus, the simplicial homology must also be the same. Okay? So they both have the same set of critical triangles, they both have the same sets of flows. Therefore, they have the same Morse homology. And so that's how you prove that they're the same, even though we never actually compute the Morse homology. So when we do the distilled Viator strip, so this is the number of two simplices, okay? We get a much, much smaller complex, okay? So here is a set of random points in the cube. So we're looking at a three-dimensional sort of point cloud. And here we have random points in the two-sphere. Now, yes, it's in R3, but it's really lying on a two-dimensional submanifold. And notably, the number here is kind of like 2n, and the number here is kind of like 3n. We can't prove this, but we have conjectures. The key thing is it's much smaller. Now, it takes a long time to compute. Partially because it's highly parallelizable, embarrassingly parallelizable, and we have not parallelized it. But it's extremely memory efficient. And that is actually the real blockage in terms of computation at the moment. So there's nothing that's stopping us from combining that distilled Rips with the trick of knowing when to stop. We haven't done that yet, but you can. And that's my second last slide. I just want to finish with thanks to everyone and to mention the relevant resources. So the first paper talks about the reduced Rips and why it's the same. And the second takes the reduced Rips and distills it. So the first is available already on arXiv. The second was submitted to arXiv this morning. And if you would like more details of a more technical nature, I highly recommend going to Musashi's talk this afternoon. And that's all I got.
All right, thank you, Kate. Are there questions? Question here. Sorry, here comes the microphone. Just a moment.
All right, so you talked about links earlier, like linking in proteins.
Oh, yes.
Is there a way to see linking from, like, topological linking, like linking in R3?
You know what? I am going to pass that question to Agnese over there, who's an author of one of those papers. There's a microphone coming. Delegation, it's great.
Between different chains, you mean? I think in principle you could. When you're working with spatial linear curves, in particular proteins, I think one first-dimensional persistent homology is quite effective at finding like local structures. So yes, I mean, I haven't tried that. I only looked at like knotted stuff, but yes, in principle, I think you could.
Okay, other questions? Got one right there, and then back there.
Could you elaborate a little bit about the applications to cosmology?
No. I will be completely honest, when I was writing this talk, I went persistent homology, and then I looked at Google Images, and I liked the look of the image, so I went to it. It is something to do with mass on the galaxy universe level, and looking at its structures. And it mentioned dark matter halos. I don't know what they are. I got lost in the astrophysics quite quickly, I have to admit. So I'm afraid I can't help you.
But what was it trying to show?
I think it was something to do with calculating Fisher coefficients, which is some astrophysics thing. I can't help you, I'm afraid. Oh, you know.
It basically lets you compare simulations with data observations. It's a way to characterize the data.
I love this. Every question goes to somebody else.
Oh, sorry. It's basically a way for you to compare geometric structure. So you do simulations and you want to compare them with your observations. And so persistent homology gives you a way to do that comparison.
Now, the question I want to know is, whatever the data is, whatever your interpretation of the data is, but does that tell me something about the topology of the space-time?
Yeah.
That's all right.
Okay, we can chat. I'll chat afterwards, yeah.
All right, there's a question behind you, and then one up in the front.
Yes, so I wanted to pass from the question of persistent homology to the question of persistent homology software. Mm-hmm. So how does one go about funding a set of research software engineers or some facility for maintaining, updating and enhancing software once you've gone about publishing it and it turns out to be useful?
So there are, historically, most of them have been research groups. So, for example, Goody is run by the INRIA group at SACLE, and so they have government funding and they do it as part of their research. And like I know that so RIPSA is also a group. There are some startups that have started to happen that have developed software, but they're more of a minority. So usually someone gets a big grant, and it's done within a computer science department. Yeah.
Okay, question up here.
So I'm very curious for the plots you have that appear to be linear.
Oh, yeah.
Is it, do you suspect, theoretically, you can actually prove this is
Okay,
going to be
so
linear?
think about points in the plane. Okay, I have points in the plane, and I create the RNG, and it splits up into nice little polygons, and then I'm going to fill those polygons up with triangles. So if I take a polygon and it's got m vertices around the end, I'm going to need m minus 2 triangles to fill it up. And then if I do the plane, I'm going to have a polygon to my left and a polygon to my right. And so that means that every vertex is going to appear in 2 polygons. And so I would expect, if I have n vertices, that I will need 2n-ish triangles. So if I have points in the plane, I expect that to happen. Now, if I have points on the sphere, the vast majority of my classes are going to be within the kind of sphere, and then there might be some big ones going through the middle. Okay? So the vast majority is going to look locally like the plane, which has that polygonal split up. So that's the intuition as to why I would expect it to be linear.
But just follow up, that's in expectation. Do you suspect this kind of bound is going to hold theoretically?
That is my conjecture, but I mean, maybe you need a higher order term as well, I don't know. I mean, I could prove it for points in the plane, but that's not very useful.
Okay. Are there other questions? Okay. Maybe one more?
Yeah, beautiful talk. So one case that's of interest, of course, is not data that's geometric, but we just have like a finite metric space.
Mm-hmm.
Have you done experiments in that setting? I would expect it maybe.
I wouldn't expect linear in that case at all. The code for the distilled has been written in such a way that you could put in any symmetric matrix as your input, I believe, but it's still very much work in progress. So it's not yet at the stage of implementation that we're ready to simulate, experiments at it to see what run times and complex sizes are yet. But yeah, I expect it will certainly be not linear for the arbitrary symmetric matrix case, but much better than reduced. Yes. Oh.
Okay.
I'm just wondering, say in R3, will Euler characteristics be helpful?
So the Euler characteristic will not tell you anything that is persistent. It will only ever tell you information at a single time step. Radius.
At least some reductions of your calculation.
I'm not aware of any use for it in terms of the persistent homology. It's something you can infer from persistent homology rather than the other way. You definitely lose a lot of information. Yeah.
All right. Well, if there are no other questions, then let's thank Kate again. And we have a gift for you.
Exciting. Oh, yeah.
Thanks again very much.
Thank you.
This is a quick announcement for anyone going to the computability session. We've had to move your room from 303B7 to 303B13. It's in the same area and there are signs and people up there to direct you. It's just for this session. So, thank you. Sorry to barge in like that.
I think I muted it.